Okay, for this problem, you just want to do the normal thing. So you want your beta, what else? Lambda, and your length. So the first step is usually just using that telegraphic equation I showed earlier. So plus e to the minus j beta z plus and then with gamma, oops, gamma equals, this turns into right. And then from here, you want to start reading the problem actually. So you get zg equals 50, epsilon r is 2.6, length of the transmission line, which is equal to 1.r24 meters, and then vi, you want to convert this to phasor right away. So it has a phase shift, so it's going to be 100 e to the negative j 0.760773. And then this is just 100 because it had 70, I mean, because it has no phase shift. 70 volts. Okay. So here, what are you given? You're given the voltage across here, which is 70, and then you're given the voltage at the input, which is 100 e to the negative j, 0.760773. So these equations I wrote down a bit ago, they're gonna come into play. This one, right? Because you're given the voltage at the load, and then you're given the input voltage. So this will turn into this, which is your entire transmission line, which is this equation. So your VI is equal to your VL, or your VL, I'm sorry, equals to V naught plus 1 plus gamma. So you have this. And then for the other equation, well, you're going to turn it into a length to get your VI, which is equal to your Z equals negative L, is equal to this. L, let's turn it into a positive. Standing into negative J, beta C. Um, Part A, he wants us to find ZL. Part B, VG. So what are all the equations that deal with ZL? It's gamma equals ZL minus E naught, ZL plus Z naught. And then your Zn equation is reliant on that uh, normalized load impedance, right? So looking up the information he gave us, which are the two voltages, we can find out immediately that we have two equations and two unknowns. So we're gonna go ahead and do a system of equations to get this gamma part. And with this gamma, we're going to be able to find our load impedance for VV naught plus. Yeah. So since you already, so you can just plug it into the calculator straight like this if you know how to use a system of equations function. It can also do a complex solve for system of equations, or you can also solve for V naught plus twice. So for here, it turned into V naught plus equals VL over 1 plus gamma, right? Because you're dividing this on this side. And then for this one, we'll turn into VI over e to the plus j beta L. And then what you can do is just set these two equal to each other since they're the same equation. So you divide this whole thing on this side. So you get a V naught by itself. And then you just set them equal to each other. And here you have VL, VI, you have your beta, you have your length. You're just missing gamma. And you have gamma on both sides. So just seesaw for this one. This is going to give you
We don't have to.
let me see. Yeah, off the dome, I think it's this. So it's 2 pi f. This is your omega, right? Omega t. So you just plug in this. Your epsilon r is 2.6 divided by speed of light, which is meters per second. Um, so you do end up getting a beta, right? I already have your link here. Your gamma, right? And
If you know is this thing.
yes. So you should come away with this. And then for your V naught plus, if you did the system of equations method on the calculator, you should also get this. Oh, one.
Once it's all good, you go back.
Yeah, if you do this method, you can just plug it back in into this equation, right, and get your V naught plus. Or if you did it the system of equations on your calculator method, it'll just give you both outright at the same time. And then from here, you have your gamma. You just plug in into this equation where this is 50 ohms, given the problem. And then that's part A. Yeah, this is the answer in polar.
So do we want that in polar or does it matter?
It doesn't matter. Rectangular or polar.
We just all move the small grip in the middle.
Um, it does matter. On the calculator, keep all of them. I think the max on the TI is 12, so keep all of them. On the actual workbook, we just do like 4. This one?
Yeah.
1.098742. And then part B, he wants us to get the voltage at the generator. So we derived that equation earlier, right? So VI is equal to our VG Zn plus Zg. All right, we have our VI. We're looking for this. And then we don't have this also, but we can get it with our ZL, right? So all you want to do is just plug in that Zn equation. ZL plus J tangent theta L 1 plus J ZL, where ZL is normalized impedance, right? And then you get your Zn value, you plug it in here, and then you seesaw for VG, and you end up getting a final value of VG equals 6. At 21302. Easy? Which one?
Plug it back into, so there's two ways, you gotta do the system equations or the seesaw. So when you do the seesaw, where do you plug it back into?
So you're gonna get gamma, right? Whenever you seesaw it. So you can plug it in into any equation, it's fine. You have all the information for both anyways. Um, but as you can see, for part B, V naught plus wasn't needed. So it wasn't too important in this situation. If you do end up needing it, you already have your gamma. So you can just plug it into this equation because it's nice, small, and simple. Any other questions before I move on? Yeah, we're going over like 4 problems today. So this is what you were asking earlier. Um, so does anyone actually know what S11 actually means from the lab?
It's like, yeah.
Sort of.
I think the S2 one is, pretty much saying V out over V in. Like that.
Is it the input? Is that the input?
So you can pretend like it's port 1, port 2. Um, so if you send a signal here, this is your S21. If you send a signal this way from port 2 to port 1, it's your S12. And then power that you send from port 1 that doesn't immediately go here, it goes back here, right to the sender, is S11. And power that gets reflected back the same way at port 2 is S22. So you can kind of think of this as your V naught plus, sort of. If you're sending the wave this direction, and if you're inputting this direction, this would also be your V naught plus. It just kind of depends where you're inputting the wave into. So from port 1, this would be your V naught plus, and this would be your V naught minus. If you're putting it from port 2, this would be your V naught plus, this would be your V naught minus.
So S11 is like Z.
No. So it has something to do with that, right? Because it's asking at this specific location at port 1 only, what's going on. So how much power is being transferred back whenever you input a signal immediately at that moment, right? Um, so the general equation that he gave y'all in the lab should have been this. And this is because whenever you shrink the circuit down, in transmission line theory at least,
It's like the L line, same form, same,
you're pretty much measuring this point, right? You input a signal here at point A, and you want to measure how much is coming back at point A real time, right? So this is your S11 measurement.
A to A prime, right?
Yeah,
And you're measuring what exactly the voltage from AE to A11?
in this case, yeah,
So just your,
the one that gets returned.
isn't that not just VL?
What do you mean? No, because load voltage, like
Oh, this is.
in the actual transmission line circuit, it'd be over here, right across this point.
Yeah.
But this is all condensed down. So you just want to start off with this point immediately, right? So he gives you S11 here in the problem. He gives you Z naught also connected to a 50 ohm lossless transmission line. So you're able to get seesaw. Again. Yeah, which is your characteristic impedance.
Is not VA, right?
It's reliant on ZA. Because in the normal the problem we did before, we shrunk it down to get ZN, and it was dependent on ZL. So from here we're going backwards, right? We're getting our ZN first, and from there we're able to get our ZA. Was 89. Is it? Oh, I'm sorry. Yeah. 69. 2, 4, 37. ohms. And from here, you just plug it into the normal ZN equation, which in this case, it's ZA, right? Impedance of the antenna. Should be normalized that. That's J tangent. J. So you get ZA, which is equal to that over the characteristic impedance, which will give you 9 point. Is probably
For what, too?
0.1924 37. Yeah. So for part B, you're given BI. So you already know using telegrapher's equation. Um, that was ugly. BI. So equals negative L. And then choose your V naught plus e to the j beta L plus gamma e to the j. Yeah. So he wants you to find the voltage across here. So your power equation is going to be P equals 1/2 real of your voltage across the antenna and your current across the antenna conjugate. Yes. Let's see once. Okay, so now we're able to solve for our gamma right here, using since we already got ZA from part A. So yeah, ZA, and then we're able to plug it into this equation and see solve for this one. If you don't want to see solve for this one, here's the normal equation, which is VI um, over e to the j beta minus j beta, which can also this one characteristic the characteristic impedance. So you see right here when it tells you it's connected to a 50 ohm transmission line. That's your characteristic impedance for the line. Yeah, you're good. You're good. It'll be important later on. Don't worry.
What was that one you were saying, the other equipment?
This is another form if you don't want to see solve using this equation because you're given VI, right? In part B, he tells you it's 10 volts.
Yeah.
So you already solved your gamma from part A using this one. So you have everything except your V naught plus. Right? And then the voltage across the antenna is whenever Z equals to 0, right? So the exponents cancel out to 1. So you get your V naught plus 1 plus gamma. I do not. So I'll probably do it like when I get home or something, just to make sure y'all got the right numbers too. And then you're able to get your current with this, which is your voltage over the impedance, right? Ohm's law. And then you want to plug it into this equation to get your power. Remember to take the conjugate of only the current for this formula.
Like for example, we have A plus BJ, conjugate is A minus BJ.
Yeah. I'll write that down. That gamma. But yeah, that's it. That's it for this problem. Are there any more questions regarding the process of how to go about it?
If you use seesaw, it's under the column.
The variable.
So, as usual, we want to start off with the telegrapher's equation. We're given ZG equals 50. So this right here is 50 connected to 50 ohm lossless transmission line. So Z naught equals 50 ohms. Mu equals mu naught. Epsilon equals that. You can grab your epsilon r equals 2.1. Given length, 1.724 meters. Given voltage at the generator, which is, turn it into phasor, which is 100. And then you're given the voltage in the middle of the line, which is 34.252 minus her E minus 2.01 J. Determine ZL. What is this? We write this to the standard equation, so we know. And then you're pretty much going to be ending up using this equation multiple times, right? Actually, one time, because he gives you the voltage across the line. So you're immediately able to transform this equation to fit this equation. So what this is saying is that Z equals negative L over 2, which is equal to V naught plus E to the negative J beta negative L over 2. So this turns into a positive. And the other one turns into a negative. So what do you know so far about this equation? You have this, don't have this. You have this, you don't have this, and you have this.
So.
So you have two unknowns, right? Again,
I,
well, you're not given that.
the V,
You're given VG.
oh. I is VG minus VZ. Like, oh wait, no.
So this is kind of where you start uh, kind of looking at your formula sheet and seeing what involves VG so you can use it, right? Because he gave it to you for a reason and not VI. So what formulas already involve VG?
Oh,
Yeah, so it'd be VG, Zn, Zn plus G, right? But you don't have VI and you don't have Zn. You can't get Zn because it's dependent on ZL, which he didn't give you.
so we have V in unknown, VI unknown, and V not plus unknown, and
Yeah, man,
so four unknowns.
two equations. You can't do it.
So what you guys
So-
do is
What else is this also equal to? What else is this also equal to?
not plus
Give me the version with the L.
e to the j beta l plus e to the minus j beta l.
Right?
And then you got get rid of z in, so that's one less unknown, and you get rid of bg at final. There you go. So three unknowns,
Pretty much same spot, right?
two unknowns. Wait, no, we have two unknowns and two equations there.
Where?
VI, lost on that. Three unknowns, two equations.
Yeah.
Narrowed it down. Okay,
So you look into you go deeper in the back, right? Just start looking at your Z and equations.
so E in means the out, and means the L. But
Alright, so Zn equals Z naught 1, what was it? CL plus J tangent 1 plus J. Alright, it's also equal to something else. Just 1 plus minus
oh, okay. So gamma.
gamma e to the negative 2J beta L. So now, with all these equations, is there a combination where you can get two equations with only two unknowns? So first, you always want to start off with form the equations in that such a way where there's only one unknown on each side, right? So you remember how we rearranged the V naught formula earlier because we didn't have it. So we put it on one side and we had one unknown on the other side.
We already have that right there. Z in equals the Z out.
And so there'd be V naught plus, right? You're dividing this and putting it on this side because he already gave you that.
So you be I. So,
And then is there any way we can do it given that VG formula? Since we're given the value of VG, is there any way we can manipulate this formula to make it look similar to this one?
oh, I see. What you do.
So you have your VI equation, right? It involves VG. And you also have this version of the formula, which has the V naught plus. So you're able to divide this over to this side right? So you have another V naught version you can use with the VG value he gave you. So it looked like this. All right. But if we set these two equal to each other, there's still a problem, right? We don't have gamma and we don't have Zn. So we're solving for two unknowns using one equation. The next step here would be to look at any of these variables that we know we can swap out. And the one our most likely candidate is going to be our Zn, right? Because if we look at the Zn formula, we have everything else except gamma. And if we were to plug this in, our only missing a variable would be gamma, and we can get gamma to solve the whole circuit. Well, these are two versions. You can write the same thing. It tells you the same thing, right? So your gamma for this one is also dependent on ZL, but you can get your gamma first, like we did in the previous problem, and then use that gamma to get your load impedance. Welcome to Emag. I hope y'all didn't slack off in linear algebra. So this would be a big bad boy. So which is equal to this, and then we'd be plugging in for Zn this equation. Would be Z naught 1 plus e to the minus 2j beta L 1 minus e to j beta L. And then you write the same thing all over again. 1 plus gamma e to the negative 2j beta L 1 minus plus Zg. This is actually the farthest you can go with this problem on the actual exam.
Oh, really?
Yeah.
That's it? That's the answer?
So you kind of found out that this is only solvable through like MATLAB. And you actually get two different equations, two different answers, but one of them actually works because of the properties of gamma. So if you got this far on the exam, then
That one.
you get like, yeah, you pretty much gave you all credit. So if you want to write a MATLAB program doing all this, go for it. You'll get a better intuitive understanding of what's going on with this specific problem, at least. Crazy enough to do that, you end up getting this ZL. All right, but you're solving for gamma first, or which you know, and then you plug in this gamma into this formula to get your ZL. And your ZL is going to be this exact thing. This is part A. Yeah. Some light, some light. And then, yeah. So for uh practice purposes, right? Whenever y'all are just practicing and y'all finally get to this step, um, I can just skip because it gives you the answer in the PDF I handed out. So you can just work from there. Because if you keep going, it's still solvable with the calculator. So it's just more practice on your app. With the part B, which is just finding out the power delivered across the load. So to do this, we're gonna need all our voltage characteristics from the generator and the load. So first thing first is you want to get your VI, and the way you solve your VI, right, is either getting your V naught plus, gamma, or your Zn. Since you already have VG, ZG, all you're missing is your Zn, which you can immediately get from the answer. You just plug this in into the Zn formula, plug it in here, and get your VI. So that looked like Zn, which is you get this, right? And then you plug it into the I equation, which will net you this VI. And then with that VI, you're able to solve for your V naught plus. So it's VI 1 over E to the J beta L gamma e to j. Mhm. Yeah. And then you're able to find your voltage with this voltage amplitude. You're able to find the voltage across the load, which is that simple formula, plus 1 plus gamma. This is the gamma you solve for um, in that huge mess of an equation, which will net you 59.566 e to the j 1.92. And then with this, you're able to get your current VL over ZL. Plug it into the power equation. 1/2 the real part of VL times IL conjugate. And for this one, I got but he has written down 22.48. No, 2. So from the he got this exact answer because he was using MATLAB, which carries way more than 12 decimal points. Calculator can only do 12. So don't be shocked if you're like, I would say give it 3 watts plus minus for your answers. If you're within that range, he'll still give you full credit. But yeah, that was part B. And here's the next one. By the way, did y'all have any questions for the previous one? It was straightforward after that big equation.
Was it intentionally made it this way, or just put the numbers? The result will actually,
Kind of both.
I thought he probably knew,
Kind of both.
because he knew what was given was not.
Well, yeah, but he's not gonna, sit down and do it by hand. He's gonna do it MATLAB. If we can do this, it's solvable. Okay, won't put on a test. So I don't think he tested it by hand if it was solvable by hand. So, but he will try and put something as difficult as that on the exam, which is probably why you need to know how to just derive everything from this single equation. If you can do that, you'll be fine. You can just see it as a load. It's just another load at the end of the day. He's just being specific about it. It doesn't matter. So for this one, he tells you diagram below shows an antenna of impedance ZA, right? ZL, same thing. Connected to a 75 ohm lossless transmission line. So characteristic impedance is equal to 75 ohms. Length is 6.37 meters. So 6.37 meters. measurements at the input of the transmission line using a VNA with a port impedance of 50 ohms give 0.1 e to the j 0.3. The wavelength of the transmission line is 15 centimeters. Determine ZA. That's what we're looking for. So anytime he gives you S11, you immediately want to use that one formula, right? Because you're given S11 and you're usually always going to be given the characteristic impedance of the transmission line. So the only thing that you'd be missing is that Zn, right? So S11 equals Zn minus Z naught, Zn, Z naught. And usually I like to explain it whenever I'm doing double O problems, but you always, all these equations are with respect to what you're referencing, right? So if you go back to this one, you're given the voltage at the middle of the line, right? So using here, you're going to plug in L over 2. So instead of using just JBZ, you're going to plug in that negative L over 2. And it's going to turn into JBL over 2, which is a distance from that, which is the specified distance of the voltage. So if he were to give you at this point, like 3 ports, this will turn into 3 ports. It's still going. Okay. Yeah. So remember, most of the information he gives you is for a specific reason, because it's meant to be used, right? So in this case, he gives you the measurements at the input of the transmission line using a VN. Okay.
Seeing something on the keyboard maybe?
I don't think so.
Oh.
I'm not even putting pressure on this piece of paper, so I'm putting it down. It's still recording. Yeah. Anyways, I lost my point. I lost my point. Oh, yeah. So just be careful actually reading the problem, right? Um, so S11 particularly pertains to the actual VNA measurements he's taking from the lab, right? And I don't know if you remember in the lab, when you're doing measurements, one end is a transmission line cable and the other end is shorted out with a 50 ohm transmission line off transmission.
That little cap.
Yeah,
It's short.
it's a short end, right? So for here,
But it could have been open.
I'm not touching the keyboard. Anyways,
These are usually my people messing like it's not. Yeah, correct.
that's unfortunate. Okay. So the point I'm trying to get to is that all these equations are referencing a specific point in what you're talking about. So for this one, S11, VNA, you're going to use that port impedance for your characteristic impedance. Right? So your Z naught is 50 ohms. And anything you use, any formula you use with the transmission line, so your ZN formula, has that characteristic impedance also, you're going to use 75 instead, because that one's dealing directly with the transmission line itself. So for here, it's going to look like 0.1 e to the negative j 0.3 equals Zn minus 50 plus 50, right? And then you're going to obtain your Zn. To 60.55 to 21 e to the negative j 0.0596 ohms. And then sort of like the last one, the last S11 problem, we're gonna go ahead and solve for our normalized load impedance. So using this equation, dA plus J tangent beta L, 1 plus J dA tangent beta L, where this is 75 ohms, right? Because this equation, you're using property of the transmission line to shrink it down. Yeah, which is equal to ZA or Z naught.
And the Z equals Z equals Z naught, we're using the same problem, Z naught, so, yeah.
This one? This one? We're using 75. Because everything, right, that 50 ohms was only useful for the specific VNA, right? So everything dealing, now that we got the information we needed from it, ZN, everything else that we do now is with respect to the characteristic impedance of the transmission line, which is 75. So here, this equation, you're shrinking down this load to point A, right? From point B to point A, you're going to use 75 ohms. This one is normalizing your load with the characteristic impedance, right? To get your normalized load impedance. So this one as well will be 75 ohms. Which will give you 16.2059 e to the j 0.0333. Right. So just make sure you just make sure not to confuse the two port impedances he gives you. So for everyone last semester got confused with this port impedance of 50 ohms and the transmission line characteristic impedance of 75 ohms. So they just use 75 for everything. When instead, right off the back, you're dealing with the VNA measurement. which tells you it has a port impedance of 50 ohms. And if he doesn't specify anything like he did in the previous problem, assume characteristic impedance of the transmission line equals port impedance. So 50 ohms. If he doesn't tell you port impedance, 50 ohms. And then for part B, using parameters and ZA from part A, determine S11 again, using a port impedance of 50 ohms for two antennas connected in series using two transmission line segments shown in the following figure. So what this is and gonna end up looking like is that you're gonna connect another one here. Where this is also ZA. And then the length is also 6.37 meters. And then this is more of your classic double load problem. Yeah. So whenever you're measuring S11, you're taking it from the input, right? So the goal is here is to shrink this transmission line down all the way to here. Or this is your ZN, right? Of this entire transmission line. So goal is A, or this is B, A, C, condense down from B to C. So this is they're starting off, right? Three different points in the transmission line. Goal is to shrink this down from C to B. So that A, B, using the ZN 1. And then at point B, there's going to be two loads now, right? Your original ZA, and then the one you just shrunk down. So you're using your ZN formula with respect to everything that's going on between point B and point C, right? Because you can't go straight from C to A because this load is preventing you from doing so. So with this, you have two impedances in parallel. You just want to add them together to get an equivalent version. And then now you're stuck with only one load at point B, which is your Z equivalent. And then you want to condense this down again, just so that there's only one load at point A, using the ZN or using it again second with respect to this load. So this isn't as big as a problem as you might think it might be, just because the way he arranged it was that you already found your Zn on the previous problem whenever he gave you S11. So this value is the same thing you'd be doing if you were to start uh from here, from point C to point B. So you can just use this value and start from here. So you'd plug in this number with your ZA and plug it in here, and then get your ZEQ and then plug it into this formula again. So what that would look like is your Zn2 would be your Z0, your ZEQ plus J tangent beta L. I'm take it easy. Plus J ZEQ tangent beta L. Right, where ZEQ is equal to this, and this is equal to 75 ohms, right? Because it's a transmission line. Um, this is going to give you the value of 34.2646 e to the negative j 0.4100. So here, now that you shrunk it down into this position, which is your Zn, you plug it into the S11 formula, right? So using the new Zn2 with the duplicated transmission line and antenna, you're able to plug it back into here. And remember, since we're using S11, we're technically on this paper using the VNA. So your Z0 will go back to 50 ohms. And then here, you should get 0.2793 e to the negative j 2.3413 volts per volt. So if you plug this into the calculator in rectangular form, you get the exact same thing. This is just polar form. It doesn't matter which form you use. He has both. Just use whatever it's more, whatever you like more. Whenever I did Emag, I was just using polar, team polar. Um, but yeah, another thing I wanted to point out is that whenever you're going from a double load from here to here, you want to use everything with respect to what's going on here, right? So whenever you're using the Zn equation, Z naught, Z alpha plus J tangent beta L, the only thing that's going to change is your length, right? Because from C to B might be different from B to A. So if you're shrinking this down from C to B, it'd be 6.37 meters, right? And then now you're at this point, you're shrinking this down from here all the way to 0.0. So you use this length, and for this situation, it just happened to also be 6.37 meters. Every time you see a double load question, never use the entire length. So that's,
So in this case,
if you use the entire length, you already,
yeah, I'm using-
no. Because you can't go from point C to point A without getting rid of the load at point B. That's why you stop at point B. They're in parallel. Combine them in parallel, right, using this formula. And then you're back to a normal single load transmission line problem.
Going from, where, route two, towards A, B, C, CN one, with that CN one formula, it's on the top, right?
Yeah. So the way this problem was set up is that you solved for this already whenever you had S11, right? And you immediately go for ZN, right? So
In this case. you're
in
trying
this
to-
case, you already did he already gave you the first part if you did it right. Uh-huh.
I think you made everyone in the room very happy. Appreciate it.
What's up?
You never want to update, so.
I mean, it's a lot, man. It's a lot. So yeah.